Very much for inviting me to share our work on the estimating of the accuracy of protein structure. This is my student's work, Alex Moorhead and Jianlin. So they are not here, so I'm going to present it. So first, I'm going to give a quick introduction to the problem. Then I'm going to describe our methods of geometric complete graph neural networks for estimating the accuracy of predicted protein structures. Then I'm going to summarize some results, then finally conclude my presentation with a few key findings. John gave a great presentation, development of the task, and the method development in the task. So I'd like to add a little bit details about the deep learning development in this field. So deep learning started in 2000, actually was introduced to protein competition in 2012 in Kazakhstan by our group. Then it ranked first in the competition. Then in 2016, in 12, convolution neural networks were applied to this problem and also combined with the co-evolution features. That's why the competition got significantly improved with that co-evolutionary features John mentioned. So that's RapidX. Then in 2018, three methods use convolution neural networks with co-evolution features, generate better competition, and also significantly show that they can improve the tertiary structure prediction. That is AlphaFold 3, ITaser, and our method multicom. Then the biggest breakthrough actually coming in 2020. That is AlphaFold 2. They developed end-to-end AI methods for predicted protein structure that reach the experimental accuracy for most proteins. That's drastically changed the whole world. Then followed up by some other methods like Rosetta Fold, ISMB language models to predict protein structure, and also extend AlphaFold to AlphaFold multimer from monomer structure prediction to quaternary multimer structure prediction. Then since then, everybody use AlphaFold in the Cas15. You see the accuracy drastically improved. That's 2022, and of course, probably most of you have known that AlphaFold 3 was released. It's a very quick method that can predict structures of monomers, multimers, and RNAs and DNAs all together. And we are actually also leveraging that resource right now in the Cas16 competition. It's going on right now. So now we can see this protein structure prediction has been dominated. Model generation has been dominated by AlphaFold now. What next can we do as a developer in this field? Fortunately, there's still some other problems for us to work on. One problem is, significant remaining problem is how to estimate the accuracy of predicted protein structures, also called the quantity assessment. So we can either predict the global quantity of a protein structure model, the overall score of that model, or we can also predict the local quantity of each residue in that protein structure. And this is very important because it's important for us to select the top models for the biological research. Also, it's very important for us to guide us to use how to use these models to solve my biological problems. So it's a remaining problem we need to work on. There are also really some methods for this problem. The traditional energy-based, statistical potential-based methods, they calculate the energy of the protein structure. However, they cannot be very accurate, and they cannot learn from the data. So they cannot leverage a huge amount of the models and their quantity we already know to build a better scoring function. And also they're already saturated. So another things we got is AlphaFold itself has its own building method, accuracy estimation method. Actually works pretty well. So you can use such triangular models. But however, it also has a problem. That is, it's method specific. It only works well for AlphaFold predicted models. And also it's not independent because that score is generated by AlphaFold when it generates the protein structures. So sometimes it tends to overestimate the accuracy of the predicted protein structures. And also that score cannot be used to compare models from one generated by one method from another method. And sometimes it fails. There's still some room for the improvement. That's where we can do more. And of course, then the future direction would be developed machine learning methods. There are already some machine learning methods have been developed for estimating the quantity of the protein structure. But most of them actually use the statistical features like a secondary structure, soreness accessibility, contact information to estimate the quantity. They are actually haven't leverage the rich geometric information in the protein structure, atom interactions, geometry, their orientation, those information. So that's something we can leverage to improve this kind of methods. Another thing is that most methods have been designed for estimating the quantity of the tertiary structures. Much fewer methods for estimating the accuracy of the quaternary structures. The reason is that there are a lot of the tertiary structure models, not many quaternary structure models for training those kind of machine learning methods to predict quantity of the quaternary structure models. How can we overcome that challenge? That's what we try to work on in this work. So basically, we try to develop a unified geometric deep learning model for estimating the accuracy of protein structure. So the input is a structure, can be a tertiary structure or quaternary structure. And we're going to use the geometric deep learning to learn the representation of this structure from those information, then try to predict the quality score of this model. Particularly, we are interested in predicting the local quality score, basically the measured by LDD score, that is local distance difference test score. So basically, calculate the quantity of each residue in that structure is based on the distance between that residue with other residues. If the distance is close to the true distance in the native structure, you get a higher score. Otherwise, you get a low score. And these local quality scores can be used to average together to get the global score. That's one way you get a global score. So that's what we try to do. So basically, we try to directly use the 3D structure as input. However, using 3D structure as input has a challenge, because when we rotate the protein structure, your input XYZ coordinates change. When you translate it, it will also change. However, the essential features of protein structure do not change. The quality do not change. So our models need to be able to recognize those essential features regardless of the translation and the rotation of the 3D object. So that kind of models, we call those machine learning models are invariant or equivariant models. So they invariant or equivariant to translation and rotation. So here, I'd like to use two simple examples to illustrate this idea. What's invariance? Invariance means that's a face recognition. So if you rotate your face, if your machine learning models capture the exactly same features, no matter what the orientation is, that is invariant to the rotation. If we cannot achieve the invariance, you can also achieve the equivariance. That means if I rotate my face, my features also is rotated in the feature space. The similar features have been captured in different rotation place in the feature space. Then your model can still work well to recognize the essential features. So we actually designed a geometrically complete graph neural network for this problem. Here's an overview of this method. So here you have a 3D protein structure. We treat it as a 3D point cloud. Then we use each node to represent one residue, simplified representation. So we can actually construct a graph that connects the nodes that are close to each other. Then we also have, for each node, we have some node features describing the residue and its position in the protein structure, and also the edge features describing their distance and orientation, direction. And also we have another thing that is unique to this method. It's called local frame. Basically, it captures the relative orientation, direction of the any two contacted residues. Then give this as the input. We use a graph neural network, geometric complete graph neural network, to update the features in the representation of this protein structure. When this representation reaches a higher level, good enough for quantity prediction, then we use it to predict the quantity of every residue. And these predictions can be summarized to predict the overall quantity of the entire structure model input. So that's the overall pipeline of this method. Now, I'd like to describe any details about how it works. So give a protein structure, tertiary structure, or quaternary structure. We build a graph to represent it, actually use the KNN approach. Basically, each node is connected with its 16 nearest neighbor in the protein structure. Then for each node, we have some node features. Some features are already invariant to the rotation translation, like residue type, position encoding of this residue in the structure, and virtual dihedral and bond angles of the carbon alpha trace, and residue backbone dihedral angles. And also we have some optional features like the residue representation generated by large language model, ESM model. And also we can also use AlphaFold to predict the PLDD score as input. That's one input feature. That's also optional. We also have some edge features. One edge feature, obvious edge feature is distance between the residues, right? How close they are. And we also have the direction vector describing the connection between the two carbon alpha atoms in the protein structure. So those are the features we are using for each residue. Now, then we're going to use a geometric deep learning network to update these features, use these initial features as input. So we use a graph convolution approach. Basically, if I want to update features on node I use its previous features at a layer L-1, and also is features of its labels, J, the edge features between I and J, and a local orientation frame. That's what I'm going to describe now in details as input to generate the new features. We repeat this process until you get higher level features representing the protein quantity. Now, here's a little bit details about this approach. So here at the layer L-1 layer, so we have scalar features, vector features describing the nodes and the edges. We also have a geometrical local frame as input. Then we use a series of neural network operations to update these features to generate the new scalar features and vector features. So like downsampling, upsampling, all those kind of the concatenation, all kinds of the operation. I'm not going to get into details, but just know you have input features, you get a more higher level output features. But I'm going to describe a little bit of key information that distinguishes this method from other graph neural network methods in the field is using geometrical local frame. So basically, this local frame contains three components: alpha ij, bij, cij. Alpha ij basically is for each node residue, you have x position xi, xj. So this alpha ij is a vector pointing from j to I. So that vector represents the direction, and also we also use their cross product between the two xi, xj. That represents a vector perpendicular to this one, this plane defined by xi and xj. And finally, alpha ij cross product with bij, you get another vector perpendicular to the plane defined by this. So these three vectors actually capture the complete geometric information between the two carbon alpha residues in the protein structure. That is different from this early methods that only use this one, alpha ij, that lose the orientation such that it cannot capture the chirality of the protein structure. So that's why this method is geometrically complete method. It also achieves the equivalence because if I rotate my structure, xij change, these three vectors were also rotated in the feature space. So capture the essential features. So this is the key feature that make it, this model can represent the chirality of the protein structure, basically handedness of the protein structure. Now, we get a message. Now we're going to train it. Here is one innovation. Because we didn't get many multiple coordinate structure models, so we decided to use only tertiary structure models to train this method. Then try to see whether or not it works on both tertiary structure and coordinate structure. So the data set we use is ENQA data set, and it has 4,900 AlphaFold predicted protein structures associated with about 3,900 proteins. And as a training data set, we also have about 1,200 models for the validation to selecting models. And because we know their true structures, so we already know their per residue LDD score, use them as labels to train your method to learn that relationship between the structure and the quantity. We use 3 independent test data sets to test this method. First is a monomer test data set. We got 56 AlphaFold predicted structure models associated with 49 proteins that do not belong to the same scope family with any proteins in the training and the validation. Make sure they have no sequence identity, they come from different superfamily. Then we also have the new PDB multimer data set that has 350 structure models, AlphaFold structure models, multimer structure models, generated for about 100 heteromultimer multiple targets between April and December 2020. And also we have another data set, it's Cas15 multiple data set. We generated about 250 models for each target and use them to assess method. Here are the results. First, for tertiary structure prediction results, how well it can assess the quality. So we compare our method, GCP-net, two versions with PLD scores input or without it as input, with 4 different methods, particularly AlphaFold2 PLD score, its building method. And also other methods, you can see for per residue level, local quantity assessment level. So the MS mean square error is 0.92, 0092, lower than original PLD score in terms of mean square error, mean absolute error, and also correlation. And also for the per model quality, overall quality for each model, how well that quality assessment is, we can see this method also performs best in terms of mean square absolute error, and also good correlation score with true correlation score of those true quality score of those models. So works pretty well on the tertiary structure model evaluation, quality assessment. So we are very happy about this. That's what we expect it to work. Then we also have one example. Here's one example. So here you have one protein structure. You can see this is AlphaFold's own PLD score. You think it's very confident, high quality, but actually the true quality actually is lower, medium quality for that model. And we predict the quality scores that are closer to the true quality scores. So that's what we see on the monomer structure accuracy estimation. We expect it to work, and indeed it works well. Now we try to apply this method, same method, to just assess the quality of the quaternary structure models to see how well it works. We didn't expect it to work well, but it's very surprising, sweet surprise. It actually works pretty well. So on this data set, the new PDB multiple data set, you can see in terms of correlation, space means correlation, and the ranking loss, it works better than other methods, including AlphaFold LDD scores on this data set. Then on another data set, multiple data set, multiple data set, this method actually, in terms of correlation and the specimen correlation, it ranks a little lower than original PLD score. So it's really very hard to beat the original PLD score in some cases. But in terms of ranking loss, just selecting models, it works better than original PLD score produced by AlphaFold. Another is running time is very fast. Since I'm running out of time, we also release a source code at a website that you guys can use in your own quality assessment and develop your own methods. I believe this is still wide open field. Here's a quick conclusion. We develop a method that can capture the geometric information to rather accurately estimate the accuracy of the protein structure models. Particularly, we found a very good finding is tertiary structure models can be used to train AI methods to predict the quality of the quaternary structure models. So that's solve a big problem of lacking the data traditionally. I think that's. I think I should stop here.
Thinking that before we have time for one question, but of course you have plenty of time to exchange with the speakers at lunch. But if you have a burning question, please do.
So very impressive method. I couldn't quite see, numbers went past very quickly. Are you saying you can predict accuracy better than the PLDDTs directly from AlphaFold?
On some data sets, yes, we think we can, yes. But for rigorous testing, we still need the blind test like a CASP. We are now testing this method in CASP16. Let's see how well it play out. So, but on some data sets, in many examples, we indeed say that it works better than PLD score generated by AlphaFold. That's exactly what we set out to do, right? We have to do a little bit better than that. Otherwise,
what about on Rosetta Fold 2 or one of the Rosetta Folds?
Yeah, that's another advantage of the developing such method because AlphaFold.
No, it should be independent,
yeah,
but if
yeah.
you checked
All
against
of
any
course
of the
can
other,
apply to that. Can apply to all kinds of structure models generated by
I need
Rosetta
to shut
Fold,
up.
ISMB.
I can see I need to shut up.
Yeah.
That sounds like click and exchange during lunch.
Okay.